Hi, I'm Shuichi Hirahara. I'm going to talk about excluding PH Pessiland. This is a joint work with Rahul Santhanam. Let me start by explaining the very influential work of Impagazzo. He classified 5 possible words that are consistent with our current knowledge. Here you have 5 possible words from algorithmic up to cryptomania. And for example, algorithmic is a word where P is equal to NP. The rest of words corresponds to a word in which P is different from NP, and these are further classified in this way. Cryptomania is a word where there is a public key crypto system. Pessiland is the worst possible word, and in this world, it's impossible to construct a secret key crypto system, and also it is impossible to solve NP on average. Mini-crypto is a world where it's impossible to construct a public key crypto system, but it's possible to construct a secret key crypto system. Heuristica is a world where there are efficient heuristics for NP, but NP is hard in the worst case. So these are 5 possible words, and the ultimate goal of complexity theory is to decide which word corresponds to our world. In particular, most researchers believe that our world is cryptomania, so the goal is to show that our world is cryptomania. But unfortunately, there are few progress on this question, and the researchers have made little progress so far. So what we do in this work is to propose a way to make progress. Before explaining the idea, let me mention that the existence of a secret key crypto system is equivalent to the existence of a pseudorandom generator as well as a one-way function. So we are going to use this definition. In this work, we would like to propose to study PH versions of the 5 possible words. Remember that PH stands for polynomial hierarchy, and this is a generalization of NP. Usually, when we consider 5 possible words, we consider polynomial time computable public key crypto or polynomial time computable pseudorandom generators. But in the PH versions of 5 possible words, we consider PH computable public key crypto or PH computable pseudorandom generators, and so forth. In the original version of 5 possible words, there is a significant implication to cryptography, but our version has no implication to cryptography, unfortunately. But we believe that these possible words are completely theoretically interesting. Our main result about the PH versions of 5 possible words is that we were able to unconditionally rule out PH Pessiland. Specifically, we were able to show the equivalence between the existence of a PH computable pseudorandom generator and the average case hardness of PH. As a consequence of this equivalence, we can show that this statement is false, and therefore we can exclude PH Pessiland. We believe that this result is conceptually interesting because if we consider PH Heuristica, we still don't know whether we can exclude PH Heuristica or not. Moreover, if we consider PH algorithmic, it's actually equivalent to the standard version of algorithmic. So even if we consider PH versions of 5 possible words, it doesn't so trivial to exclude this word, but in the case of PH Pessiland, we were able to exclude it unconditionally. Let me mention previous work on PH Pessiland. In my previous work, we showed that PH is hard on average if and only if gap-mincated PH is hard in the worst case. Here, gap-mincated PH is a problem of approximating PH oracle time-bound column complexity. And moreover, we were able to show that these conditions are equivalent to the existence of a PH computable hitting set generator. In particular, this result means that excluding pH heuristica is actually equivalent to proving NP hardness of gap mediated pH, which is still open. In the previous work, we actually used the notion of errorless average case notion, which is denoted by average P, but in this work, we instead investigate error-prone average case compressed of pH, which is denoted by Heury BPP. Let me state our result more formally. If we consider PH Pessiland, there are at least two ways to define it. So we can consider uniform adversaries or non-uniform adversaries. We were able to unconditionally rule out both of these versions of PH Pessiland. More broadly, not only we exclude PH Pessiland, we can present equivalence between several statements. For example, the existence of pH computable pseudo-random generator is equivalent to the average case hardness of pH, and it is moreover equivalent to the average case hardness of mediated pH. This means that mediated pH is distribution of pH complete even in an error-prone case, whereas the previous work shows distribution pH completeness in an errorless case. Now let me state our result in the non-uniform case. We can prove the following equivalent. The first statement says that pH is average hard with respect to the uniform distribution against polynomial size circuit. The second condition shows that mediated pH is average hard with respect to the uniform distribution. So this means that mediated pH is average case complete for pH. We can also show that these are equivalent to the existence of a pH computable pseudo-random generator, which extends its seed by 1 bit. And if we have a pseudo-random generator which extends its seed by 1 bit, we can extend the seed more. We can show that it is equivalent to polynomial stretch pH computable pseudo-random generator. So our result shows that error-prone average case hardness of pH is equivalent to pH computable pseudo-random generator. In contrast to this, the previous work shows the equivalence between errorless average case hardness of pH and pH computable heating set generator. So the difference between pseudo-random generator and heating set generator are essentially equivalent to the difference between error-prone average case hardness, namely Heury P, and errorless average case hardness of pH, namely average P. In the case of uniform case, we can prove a quite similar result. Namely, we can show that average case hardness of pH is equivalent to the existence of pH computable pseudo-random generator, which extends the seed by 1 bit, which is secure against BPP. But when we try to stretch the seed more, we haven't been able to do this. What we can get is that it is also equivalent to the existence of pH computable pseudo-random generator that extends the seed by order log n bits. Beyond that, we are not able to prove the equivalence, but we can also prove the following. Either there is a pH computable pseudo-random generator which extends seed by polynomial amount, or there is a tally language in pH which is hard in the worst case. So it's interesting open question whether we can extend the stretch more. Namely, is the existence of a polynomial stretch pH computable pseudo-random generator equivalent to average case hardness of pH in the case of uniform algorithms. To conclude this talk, we believe that by studying pH versions of 5 possible worlds, we might be able to gain some new insight into the original version. So in particular, we believe that our result might hint an approach toward excluding the standard Pessiland, and probably the meta-complexity of time-bounded column complexity, namely min KT, would play a central role in excluding Pessiland. because we showed that mediated pH is distribution pH complete. There are several open questions. One open question is whether we can prove the equivalence between a polystretch pH computer of PRZ against uniform adversary equivalent to average case hardness of pH. Another probably more interesting question is to exclude pH minicrypto. In order to answer this question, we must formulate pH minicrypto in a theoretically interesting way, and we need to exclude pH minicrypto. By doing so, we believe that it's possible to gain some new insight into the standard version of Impagrat's 5 world. Thank you for listening.